Hi, welcome back to Statics and Dynamics. Today we are going to look at the next problem, which has to do with actually looking at tipping. Up to now, all our problems did not involve anything that falls down. All of them slid, and that has to do with the fact that they are all short, squat bodies. What I mean by that is the bodies we looked at right up to now kind of looked like this. But if I had a body that looked like this, then I'm much more worried about the fact that instead of sliding, it will tip over by rotating around this point. Tipping means rotating around one of the corners. That's what we are talking about. Okay. So rotation around one corner means we want to find out what's the moment. So this is a problem where we not only have to figure out whether it's going to slide, but also whether it's going to tip. So the problem is the following. I got a 200-pound crate. So this is 200 pounds, and we are assuming that its center of mass is here, and that's 200 pounds. And we are moving it using this system. The coefficient of friction here is 0.3, and we are going to assume that h is 4 feet. And we want to determine how much force is needed to produce impending motion. That is, we don't know whether the force will cause it to tip or whether it will cause it to slide. We just want to figure out how much force should I apply before something happens. Okay, so off we go. What do we do now? We have to draw a free body diagram, and we have to make a guess for which way it's going to move, and that's obvious, right? So it's going to, the sliding is going to be like this. So the friction force on the top thing is going to be this way. That's our assumption. Of course, if it turns out that that's not the correct one, we'll worry about it. So first thing to do is to make a decision on which way things are going to slide and pick the friction force direction. Okay, so now let's go and see if we can solve this. Here is the actual figure. I'm going to draw a free body diagram. And it looks like this. Now let me draw it kind of large. I don't want to draw a small free body diagram. Let's draw a large one. Okay, now here's the center, and that's 200 pounds. This distance is 1 foot. There's a force here, P, which is at a height of 4 feet. And there's a normal force here, N, which is at a distance x from the end, and I have a friction force that's going like this. That's the friction force. These are the forces on the body. Okay, now let's set up the equations, and that is easy to do. Sum of all the forces in the x direction equal to 0, this way positive. This way positive gives P minus F equal to 0. Sum of all the forces in the vertical direction gives me 200 pounds minus N equal to 0. Sum of all the moments, this way positive, gives me minus 4 feet times P plus 200 pounds times 1 foot minus x times n equal to 0. I'm taking moments around the point P. Okay, of course, if you take the moments around this point, nothing wrong. You can just take moments around whichever point you like. So notice I have 3 equations. So 3 equations. How many unknowns? P, F, N, X. 4 unknowns. So I need one more assumption. To solve. So our assumption, you cannot both assume something for x and f. we have to pick one of them. So we're going to assume if there is slip, then x is greater than 0. That's what it means. X cannot be 0, and f equal to mu times normal. So that's pretty easy. You can go substitute this, and if you substitute this, you will get n equal to 200, p equal to mu times normal, which turns out to be 60 pounds, and x equals, and you can solve this, minus 240 foot-pounds plus 200 foot-pounds plus x times 200, which implies x equals 40 over 200. So it will tell me that I will need 60 pounds of P in order for it to slip. Now let's look at what happens, and when that happens, the location of the normal force will be at a distance 40 over 200 feet from this end. That's what it tells me. Now let's look at the second situation, which is it's not going to slip, but it is going to tip over. So if I want to look at tipping over, everything is the same, equations are the same, everything is the same, the condition is slightly different. For tipping, equations are the same. I'm going to repeat it here. P equal to F, or P minus F equal to 0 is equation 1. 200 pounds minus N equal to 0 is equation 2. And then minus 4P plus 200 minus X times N equal to 0 is equation 3. So what happens at tipping? If I want it to tip, then my assumption is on X, and it says put X equal to 0. That is, I have reached this corner. My normal force is at this corner, my friction force is here, everything is acting at this corner. That's what I mean. Okay, that's what X equal to 0 means. N has reached corner. Let's see if that works. If N has reached corner, I will see P equal to F. We don't know what it is, but I know that from 3, so this is not equal to mu times normal, because F can be anything less than mu times normal now. So from 3 you will get 4P equal to 200, which implies P equal to 50 pounds, which is F, which is less than mu times normal. Right? So notice, for slip I need P equal to 60 pounds. For tip I need P equal to 50 pounds. So this will occur, this won't occur. Lower value is what will cause the thing to tip. Okay, that's how it works.